Hi everyone, welcome once again to another video on quantum mechanics. And in this video, we're going to talk about the interpretation of the Schrodinger wave equation as well as particle in a box. And both of them complement each other in making you understand the Schrodinger wave equation. Uh, Now, before we proceed, there are a couple of things that I want to get out of the way. Uh, the frequency with which the videos are being made are a little, staggered. Uh, I did have certain personal issues, and I do have a day job, and therefore it becomes difficult for me to, make it on a regular basis. But I'll do my best to keep that up and make the videos on a regular basis. I also got requests on completing alkyl halides. Well, technically, alkyl halides is over, but only thing is, what is left is the preparation and reactions of alkyl halides, which I'll take up once the quantum mechanics is over. So, because right now we are already doing quantum mechanics, I don't want to take a break from this. So, we'll complete it and then we will continue with alkyl halides. Now, sir, the next point that I wanted to make is that I'm going to be launching my website very soon, and the chemistryuniverse.com that you have earlier it was chemistryuniverse.com. Now it has become thechemistryuniverse.com, but the name of the site may keep changing. So right now I'm going to work on thechemistryuniverse.com, and the moment it is done and it is ready to be launched, I'll let you know in one of my videos, and then you can go and have a look at all the videos there, and I'll try and complete the syllabi as early as I can. So with all of that out of the way, let's get on with the video. This is the third video on quantum mechanics. I've titled it 12C because if you remember my earlier videos on atomic structure, I had made 11 videos. 12th was the Schrodinger wave equation, where I had only mentioned the time dependent wave equation E psi equal to H psi. But then I realized that I probably have to dig deeper and make it a more informed kind of a video, which is why this series at play. So let's get on with 12C, and that is going to be the interpretation of Schrodinger wave equation and particle in a box. Now, as mentioned before, the wave mechanical model of an electron described by the Schrodinger equation is based on the wave particle duality of electron. Now, I mentioned this earlier, but I'm going to repeat this again. It assumes that an electron is a 3D wave in an electric field of the nucleus. It contains all the measurable information of an electron in an atom, all that you can measure. It helps calculate the energy of an electron and also predicts the probability of finding the electron in a given space. So instead of locating the electron, we talk about probability of finding the electron. Now it is also consistent with the de Broglie wave equation, and if you remember the de Broglie wave equation, that was the equation where for the first time electron was given a dual nature of a wave as well as a particle by de Broglie, and as well as the Heisenberg's uncertainty principle, meaning you cannot simultaneously with great deal of accuracy find the momentum as well as the position of an electron, and we've discussed that in detail before. Now, as the electron also shows particle nature, it must behave as a standing wave. Now I'll show you a separate video of standing wave. I'll show you a video of what a standing wave is. Basically, you have two types of waves: phase that keep going up and down from plus infinity, from minus infinity to plus infinity. We call it a wave that is moving with time. It has an infinite space through which it moves. It's a progressive wave. Whereas when a wave reflects on a surface and comes back, the two waves interact, and then what wave you have is an interference of these two waves. Now that is called a standing wave. A standing wave is more localized in nature, whereas a progressive wave is delocalized from minus infinity to plus infinity. So since an electron must behave as a particle, it must also behave as a standing wave. This is why, if you remember, the time dependent Schrodinger equation is solved by a complex equation and not a simple equation, which is because of the addition of waves. We have added infinite number of waves, and that results in a complex equation. You remember you saw that factor I there. Now it also allows for conservation of energy that all equations must. The Schrodinger wave equation, being a differential equation, has infinite number of solutions. Now this is something which some of the students had asked me to explain further. So to explain this, let's take a second order differential equation. So the second order differential equation that I'm going to take up is this. Now you have this wave, okay? Now one of the solutions of this wave is y equals sine x. Now you might wonder, how is this an equation? How is this a solution of this equation? Well, all you have to do is find dy by dx first. And as you can see, dy by dx of sine x would be cosine x. Now then find the first derivative again of this, or the second derivative of y, which is d2y by dx2, and the cosine x, the differential will be negative sine x. So this is negative sine x. So this is negative sine x, and y is sine x. So what do you think is negative sine x plus sine x? Negative sine x plus sine x. This fellow is going to be 0, and it satisfies this equation. So as you can see that this is a solution of this particular equation. Now if we multiply this with a constant, that also becomes a solution of this equation. Let me show you how. You see, what happens is that if I were to do y is equal to a sine x, even this will satisfy this equation. How? dy by dx. A is a constant, so it's not going to matter. So it's going to be a cosine x. And what would be d2y by dx2? It would be negative a sine x. So negative a sine x is this. This is a sine x. Can you see it is still equal to 0? It still satisfies this equation. So even this becomes a solution of this equation. Now a can take any value. For Schrodinger's time independent equation, it can take any real value, while for the time dependent equation, it can take any complex value. This means that you can have so many values of a, infinite number of values of a's, which is why we say there are infinite solutions to a second order differential equation. Now using the Schrodinger wave equation, we can calculate the probability of finding the electron in a given space. Now the value of psi can be positive because it's a wave function. You remember wave function psi, and remember you should always have a look at the previous two videos before you come to this video, because everything is related. So the value of psi, remember, is being a wave function, can be positive, negative or 0, as it's a wave function. Now 0 actually means no wave, but negative value or positive value does not have any physical significance because it's a wave. A wave going positive is no better than a wave going negative. A trough and a crust are just basically mathematical signs. They have no physical significance as such. So moreover, according to the Maxwell's theory, the intensity of wave is directly proportional to the square of the amplitude of the wave. So if you look here, you will notice that I equals a square. So this is what Maxwell said, that the intensity of a wave is directly proportional to amplitude. Now using this logic, and to take care of the negative value of psi, we don't use psi to calculate probability. We don't say psi is probability, because remember, psi can take both positive and negative value, and negative probability doesn't make a sense. So instead of using psi, we use psi squared, which will always be positive irrespective of what psi is. So we use psi squared to calculate the probability amplitude, or you call it probability density of an electron in a given space. Now for complex functions, if you do psi square, even psi square can be complex. Again, remember, the probability should only be a value. It should not have any complex functions, any imaginary numbers in it. Say for example, if I were to have a function a plus ib, let this be psi. And if I say square of this, the square of this would be this into another a plus ib. Now this would give me a square, and this would give me abi, and this would again give me another abi, and then this would give me plus I square b, and I square is -1, so I get a square minus b square plus 2abi. But I don't want this in my squared term. So for complex equation, instead of squaring the function, we multiply it by its conjugate. Now conjugate means, let me get this thing right. The conjugate means a plus b into a minus b. So complex conjugate always means that the real term remains the same in both, but the imaginary terms becomes negative of the previous term. Now this way, what happens is when I multiply these two, I get a square and I get negative abi. Here I get positive abi, and here I get negative I square b square. I think I forgot the b square here. So negative I square b square. So this gets cancelled, and negative I square is -1, negative I square is +1. It simply gives me a real value. So remember, the probability has to be a real value. So for complex function, the square of the wave function is actually the product of the wave function and its complex conjugate. Now, again, only those solutions of psi are acceptable that are single valued and continuous. Now, if you remember, in the last video, I kept saying repeatedly, look, we will get infinite solutions. So how do we reduce these infinite solutions to a few solutions? That is done by putting certain boundary conditions. It is done in two ways. Rather, not in two ways, we follow both of them. First, we put boundary conditions, and then we normalize the function. Boundary conditions means certain conditions which will allow the wave to exist in a given space. So only those solutions of psi are accepted that are single valued and continuous. These are boundary conditions. Now, why do I say single valued? Why should they be single valued? Now, single valued because if it has multiple values, then it will also have multiple values of probability, psi square or psi into psi star, because if it is complex, the conjugate is psi star. So single valued because if it has multiple values, then it will have multiple values of psi into psi star. This means that a given coordinate, the probability density will have multiple values, which is not possible. You can't have the probability of finding an electron at a given space having multiple values. Now, again, the reason we say it has to be continuous, because all the functions of a differential equation must be differentiable. You see, the moment we say there is a differential equation, it means all those functions whose differential equation can be written means they can be differentiated. And one of the criteria for differentiability is that a function should be continuous. Because if it is not continuous, if it is just dots separated, then you will not be able to take the derivative of those. Now, these are what we call as the boundary conditions. Moreover, psi is psi naught e to the power minus kx minus omega t. If you remember, this is the equation of psi that we have derived in the last video. So what would be psi into psi star? So it will be psi would be psi naught blah blah blah. And in the case of the conjugate, remember we have to take the conjugate. the conjugate would just have the imaginary term negative. Now, if you multiply these two, you will see it will be psi naught square e to the power something, and this is e to the power minus something. So obviously, you say e to the power this plus this. Remember, you always add the powers when you multiply these functions. So exponential functions. So therefore, when you add them, they get cancelled. It becomes e to the power 0, which is 1, and therefore you get psi naught square. This implies that the probability density or location of an electron is time independent. Now, if it is time independent, again, try and understand what I said. The probability density or location of an electron is time independent. Now, if it is time independent, the advantage is its energy, momentum must also be time independent. They must also be constant. And this is the meaning of stationary states. Now, this was the concept of stationary states that Niels Bohr had used in his theory way back in 1912. Now, remember, he had said that electrons always revolve around the nucleus in those orbits which are called stationary states, where they will not emit energy. Now, it makes sense now because we know that the probability of an electron is time independent, is not dependent on time, which means over a period of time the probability remains fixed. So the energy remains fixed. If the energy remains fixed, that means the electron is not radiating any energy. So since energy in these states is constant, the electron cannot radiate any energy in these orbits. So based on this, we say the orbit of an electron gives us an indication of its distance from the nucleus. Now, so what is an orbit of an electron? An orbit of an electron will only talk about its distance from the nucleus. So whatever orbit you studied in Bohr's theory, here it is basically defining the distance of the electron from the nucleus. The orbital, at the distance of an orbit, the region of maximum probability of finding the electron is called orbital. So at a given distance, at a given orbit, the region of space where there is maximum probability of finding the electron is called an orbital. And the region around the nucleus where the probability of finding the electron is 0 is called a node. So node are those regions where the probability of finding the electron is 0. Now, to better understand the boundary conditions, we will apply our knowledge of the Schrodinger wave equation to understand how it is used. So now I'm going to do it mathematically because so far we understood boundary conditions theoretically. So let's understand it a bit more mathematically. So what we're going to do is we're going to apply our knowledge of Schrodinger wave equation with boundary conditions, and you will automatically realize how our equation becomes, how we can go from infinity to a lower number of solutions, and then we will further normalize it, which I'll explain later, and then we will be almost arriving at one single solution. Now, in this example that I'm going to show you, we will solve the eigenenergies and eigenfunctions of a particle in an infinite square well. Now, let me explain. Eigenenergies or eigenfunction means discrete values of energies or discrete value of functions. Now, again, the quantization principle comes up. That means it cannot have any continuous value, it will have discrete values. So, we will be able to find those discrete values, and for each of those values, you will have discrete functions, eigenfunctions. So, you will find in whatever I'm going to derive now that, okay, we take an example, a very simple example in which we'll put the boundary conditions, and you will find there are only specific wave functions possible, and for each wave function a specific energy is possible. So, those are the allowed states. And I said infinite square well. Now, what it means is that I have a well, I have a box where the energy is infinity outside the box, and inside the box the energy is 0, and I'll explain why we have that. Now, simplistically, eigenenergies, as I said, mean a set of discrete energies which the particle can have in space. So let's have a look. So this is also known as the problem of a particle in a one-dimensional box. This is the simplest one. So we call it particle in a box. So let's imagine this. This is my x-axis and this is my energy axis. Now, anywhere this is x equal to 0, my x coordinate. So I'm taking only a single dimension. Now, here is x equal to a, some value a. So my boundary is 0 to a. And I have a particle inside this box. So Vx is infinity here and Vx is infinity here. So what I basically mean is that the potential outside the box is infinity and the potential inside the box is 0. Now this can be understood because we assume a potential as follows. Vx is infinity except between x equal to 0 and x is equal to a, and within this space Vx is 0. Now this is understandable. We know from our experience that every object tends to move from high potential to low potential. So to ensure that the particle stays within the box, we make its potential energy infinity outside the box and lowest within the box, like a ball falling to the ground. So when a ball falls to the ground and I ask you, okay, what is the change in the potential energy? You will say, okay, it was mgh at the top and at the bottom it is 0. So don't you take the reference as 0? Even though technically speaking, it is the sea level which is supposed to be 0 for potential. But even if you are, say, in a mountain top and we throw a ball and the ball comes to the ground, for us the ground is the place where the ball will eventually fall. So we take that as 0. So by making sure that outside the box it is infinity, inside the box it is 0, I make sure the particle stays within the box. Because it cannot go from low energy to high energy unless and until you give it energy. On its own it cannot go. But it can always come from high energy to low energy. So if you were to by some means keep the particle outside the box, it will still come inside the box because the potential is lower inside the box. Now since we are looking at a quantum particle, we need to use the Schrodinger wave equation to describe the behavior of the particle in the box. Because that is what we are trying to do, interpretation of Schrodinger wave equation. So we are looking at finding the wave function psi of x representing this particle that satisfies the Schrodinger wave equation. So we are basically trying to find the value of psi of x and we are going to use the Schrodinger wave equation to do that. Okay, and we'll take from the differential value and we'll try to solve it. Now this is same as asking what are the allowed states of a particle, or can it have any state within the box? So the point I'm trying to make is that a quantum particle, can it occupy any space? Or are there some discrete spaces inside the box that it can occupy? Now we need to understand what does its probability density look like under these conditions, and also what are those allowed values? What are those allowed energies? Now all of these answers will be revealed from determining which wave functions will satisfy the boundary conditions imposed by the potential. Now what are those boundary conditions that we have? These potentials. So my boundary conditions are, okay, it cannot go out of the boundary, outside the boundary it will be infinity, inside it will be 0. So by applying these boundary conditions and the boundary conditions of the potential and the parameters imposed by the Schrodinger equation itself, we'll be able to get definite discrete solutions. Now the boundary conditions imposed tell us something about the wave function, which is that the particle will not be present wherever the potential is infinity, that we've already discussed. This means that for those regions the probability density should be 0. Meaning that if you look at this, the probability density will be 0 outside the box and would be not 0 inside the box, right? So If the particle is not there, then its probability density will be 0. That we can clearly understand. Now the probability density function is given by psi into psi star, that we already know. Now the only way this can be 0 is for the psi of x to be 0 at these regions, because without the psi of x being 0, psi of x into psi star x cannot be 0. So here the psi of x is 0, as you can see, it is 0 here. So it is 0 here and it is 0 here also. Now this means psi of x is 0 when x is less than or equal to a, and psi of x is 0 when x is greater than or equal to a. So remember, the particle cannot exist even in the boundary. It can exist anywhere inside the boundary only. Let us use the time independent. Again, we are trying to do this in a very simple way, which is why I took a one-dimensional box, and I'm going to use a time independent Schrodinger wave equation. So let's use the time independent one, and we do this for a single dimension, and let's check how we get it. So psi of x is non-zero inside. Okay. Now this is, if you remember, the time independent Schrodinger wave equation. If you don't remember, please go back to the previous video where we had derived this. Now within the box we know v is 0. So I can put the value of v as 0. So I get d2 psi upon dx2 as 8 pi square m h square e psi equal to 0, because my v is 0 now. Now I'm going to write 8 as 4 into 2 because I want to get the h bar downstairs. So I'm going to take this 4 as well as this pi square downstairs. Can you see this? I hope you are able to understand each step. And I call this as h bar. Remember, h by 2 pi is h bar. So I write it as this. And therefore d2 psi by dx2 is negative 2m h bar square e psi. Now to make the equation look simpler, let's define, now I'm going to make an assumption that the root of 2me upon h bar is k. And don't confuse this k with the k that we saw in the previous video, which was 2 pi by lambda. Don't confuse it with that. Okay. This is a new value k. And I'm just calling root of 2me by h bar as k because it helps me get this in a better form. So now if you look at this, 2me by h bar square should become k square. So this is k. So d2 psi by dx2 is this, if you remember. Now if I substitute, I'll get negative k square psi. So bring it on the next side. d2 psi plus k square psi equal to 0. Now this is a second order differential equation, which if we solve, we will get the function psi. Psi will be a function of x, and the various forms of the wave functions must be considered that satisfy this particular differential equation. Just like calculating various values of x that satisfy the quadratic equation ax square plus bx plus c equal to 0. So if you remember, when we calculate the roots of a quadratic equation, don't we consider all values of x that can solve it, that can satisfy the equation? Similarly, we need to keep all the values of psi, all the forms of the function psi that satisfies these differential equations. So let's assume that psi x is x. Now you will say, why am I doing it? I just want to prove that you cannot randomly put any equation, any function and say it is going to solve the differential just because it is infinite. Remember, infinite solution doesn't mean it has all solutions. Infinite solutions means there are certain possible solutions, but they are infinity. There are infinite number of such solutions. But you cannot put any random function and say, is this a solution of that? Because you said it is infinity. No, it's not going to work like that. So now let's see if psi of x is x. Let's check whether it satisfies this condition or not. So what will be dou psi by dou x is 1. Can you see that if I take differential of this with respect to x, it's 1. And what will be dou 2 psi by dou x square? It will be 0. Now, if it were to satisfy this condition, because remember this is a differential equation, and you say, okay, solve this and get me the value of psi so that I can look at the value of psi for the particle in a box. So somebody says, okay, how about psi of x is x? Will this satisfy? Well, we are checking it. I get this is 0. Now, if this is already 0, for this sum to be 0, this also has to be 0. So this implies k square psi is also equal to 0. Now, if this is 0, either psi is 0 or k is 0. Now, since root of 2me by h bar is k, if k were to be 0, then e will be 0. If k is 0, then e will be 0, which means there is no particle to begin with. At the same time, psi cannot be 0. Otherwise, if psi is 0, there is again no particle, and moreover psi into psi star will also be 0, which means the probability of finding the electron at that space, that potential where V is 0, is 0. And that means the particle does not exist. So the point we are trying to make is, by putting these boundary restrictions, we are restricting the number of functions that will satisfy the differential equation. See, if k was 0, then this function would be valid for this differential equation. This could be a solution. Psi of x is x. But the moment I put the boundary conditions, I realize I can't do it. I have to have the particle inside. It has to have a definite energy. It has to have a definite probability. And in this case, I cannot have both. Either k becomes 0, which means energy is 0, again no particle. Or psi is 0, again there is no particle. Psi square is 0, probability is 0. So this cannot be a valid solution by putting the boundary conditions. So as I said, this is not a valid solution to the differential equation. As we know, there is a particle. Now, rather than do hit and trial to get a solution, we can just consider the following function as psi. So what we do is we say, hey, how about this one? Use psi of x as a sine kx plus b cos x, where a and b are constants which can be determined again by using boundary conditions. Now this solution is arrived at by using well-defined mathematical rules and tools which we need not go into right now. Just to prove that this is a valid solution for psi, let's take its second derivative and check using boundary conditions. So, if psi of x is a sine kx plus b cos x, what will be d psi by dx? Would it not be a cos x and the differential of the angle, which is k, and b sine x, negative sine, and the differential of the angle kx, which is k? If this were the case, then what will be dou 2 psi by dou x2? Again, cos will become negative sine. Again, you will get another k, so k square. The negative remains here, sine becomes cos. Again, you get a k here. Don't you get this? Now, if you remember the equation 1, which was dou 2 psi by dou x2 plus k square psi is 0. Remember, we got this, and you must ensure that you keep writing it. So I'll show you that equation. Substituting this in equation 1, which is this, check whether it works or not. So what is this? This is this. So minus k square a sine kx minus k square b cos x plus k square into psi. Now remember, psi is this. If I multiply by k square, won't I get this? Can you see they are cancelling? And therefore the left side is equal to 0. So that means this does satisfy the Schrodinger wave equation. Now, plugging this equation in a one-dimensional box, let's check again. So, this is the one-dimensional blocks. So, psi of x is 0. Psi of x is a sin kx plus b cos x. And psi of x is 0 here. Outside the box, there's 0. Inside it is a sin kx and b cos x. So, since it's a trigonometric function, let's understand this equation graphically, what it means. So, graphically, if you look at this equation, now the wave function must be 0 at the boundaries, remember. Okay. So, because at the boundaries 0 and a, it should be 0. The wave function should be 0. So, if I were to take this equation, psi of 0 has to be 0 and psi of a also has to be 0. So, if I take this, now since this wave function is a combination of two trigonometric functions, let's first examine them separately, the sine part and the cos part, to get a sense of how they combine. Because first we get the sine part, then we get the cos part, and then see when we add them, what does it look like. So, if I were to take the sine part, wouldn't it be like a sine curve? And a cos part would look like a cos curve. So, this is a sine function, this is a cosine function. Now, this means that no matter what the value of k may be, sine 0 will be 0. Remember, it doesn't matter what k is. Sine 0 will be 0 and cos 0 will always be 1. Remember that. So, when x is 0, now let's look at it very slowly, try and get it. When x is 0, then the first part of the equation will automatically be 0, because when sine is 0, when x is 0, sine will be 0 no matter what k is. So this guy becomes 0, so you're only left with this. But remember, when x is 0, this function has to be 0. So a sin k0 is 0. We also know that sin 0 is 0. So the second term can only be 0 if b is 0. Look at the second term. Now this can only be 0 at x is equal to 0. Remember, at x is equal to 0, cos 0 is 1. So this can't be 0. So for x to be 0 and the function to be 0, b has to be 0. So the second term can only be 0 if b is 0. So b cos k0 is 0, and that is when b is 0. This means that using the boundary conditions, we can further simplify the equation by removing the cosine term. Can you see, I have removed the cosine term by using the boundary conditions. X is equal to 0. Boundary conditions apply. I realize a sin kx and b cos kx. B is 0, so b cos kx vanishes. So let's see. Psi of x is k sin kx, a sin kx. We also know that psi of a is 0. So now let's put the next boundary condition. Psi of a is 0. Psi of a is a sin ka, and that has to be 0, because now I replace x with a. There are only two ways this is possible. Either a is 0, again which is not possible, because if a is also 0, then there is no particle at all. So which is not possible, as the function will be 0 for all values of x. So no matter where you take the value of x inside the box, it will be 0. That is not possible. A can't be 0. The second possibility is sine Ka is 0. Now, when we look at the sine graph, we can see certain things. We will see that this is the sine graph. Look at these values. These are the places where it is 0. And the reason we are looking at the zeros because we want to know when can this be 0. This is 0. This is pi, 2 pi, 3 pi, 4 pi. So can you see for any value of n pi it is 0? This means sine Ka is 0 when k will be n pi. So for any value of n pi it will be 0. And n can be any integer. N has to be an integer because only for integral values of n is the sine value 0. So k has to be n pi by a. It follows from here. Okay. So let's examine this graphically. Psi of x is a sine kx. Remember that. Now psi of x is a sine now n pi x. I've taken a 0. Remember k is n pi by a. I've taken a as 1. You can take any value for a. A can be 1, 2, 3, whatever. I've taken a as 1. So if a is 1, then this function will become a sine n pi x. Fine. Now remember, at the boundaries, x is equal to 0 and x is equal to a. And since a is 1, the boundary conditions for x are 0 and 1 instead of 0 and a. It is now 0 and 1 because a is taken as 1. Now if n is 1, what will be the graph look like? If n is 1, can you see it is simply sine pi x? Now for values of when x is 0, this will be 0. When x is 1, it will become sine pi, that is also 0. And anywhere in between, so you know, remember, this is pi is 180, right? So between the values of 0 to 180, you will have this is 0, this is 90 degree or pi by 2, and this is pi. So can you see for n is equal to 1, this is the kind of graph you get. So for sine pi x graph, the graph that you will get will be one hump. But when n is 2, remember sine is now 2 pi x. Now x can go from 0 to 1 because that is the thing that you get. 0, it is 0. When x is 1, again it is 0. And remember, when x is pi by 2, then also it is 0. Sorry, not pi by 2. When x is 1 by 2, the middle part, because this is 0, this is 1, the middle part is half. When x is half, it is sine pi, which is again 0. So can you see, you will have one complete sine wave. And when n is 3, you will have 1.5 wave. So for each value of n, you will, for each incremental value of n, you will keep getting half a wave getting added. So for each value of n, we get a solution for the Schrodinger equation. That is the key. Now, we know that k depends on n as well as k depends on e. Remember that. K depends on n. We just said that. K is n pi by a. Remember, k depends on n. And remember, k depends on e. Remember that root function? 2mke. 2me is by whatever, by h bar was k. So, k depends on e also. So, it follows that e depends on n gives a different expression for the wave function. It follows that each value of n will give us discrete and different values of energy. Now, these are the only energies allowed for the particle or what are known as allowed states. So, what we have done is we have seen that we took an equation, it satisfied the differential equation. but put the boundary condition b became 0. Then we again put the second boundary condition. We found that only certain values of sine could be 0. So for each value of n, we got a function. For when n was 1, it was sine pi x. When n was 2, it was sine 2 pi x. If n was 3, it was sine 3 pi x. Can you see these are wave functions, unique wave functions. They are also infinity, but they are following boundary conditions. So meaning that the energies allowed for the particles are also definite, because the function is depending on n. K depends on n, k depends on E, so E depends on n. So only discrete energies are allowed. Now we can see how quantization of energy comes into play here. The fact that can only be, the fact is that can be only an integer poses quantization of energy. You cannot have n as 1.5, which is what quantization is all about. Now we have to now solve for the constant a, as without its value we do not have the precise wave function. We know it is sine n pi x. Sine part we are clear. But the fact of the matter is, if it is so, n pi x, and x can take any value from 0 to a or 0 to 1, then we do need the value of a precise value of a, using which we can say, okay, this is the function. Now to calculate for a, we must first normalize the wave function between 0 and a. Excuse me. Now we saw earlier that the solution of a second order differential equation has infinite solutions, right? Now if we get a solution for a differential equation, then the product of that solution with any constant is also a solution of the equation. We saw earlier, we saw that sine x was solving that equation, a sine x was solving, and here also a can have any value. But since we are talking about a real particle, it must be denoted by a single wave function, as the square of the wave function in a given space gives the probability of finding the particle, and this probability has to have one value in a particular space. Now to get this wave function, we use what is called the Born statistical interpretation. This is one of the interpretations that Born arrived at, and Born and Heisenberg together were able to solve and get their version of the equation of a wave, which eventually coincided with what Schrodinger had got. Now since we know that the square of the wave function is the probability of finding the particle in a given space, we put a second condition, which is that the probability of finding the particle in the entire space should be 1. See, at a given space inside the particle, it could be 0.25 probability. Somewhere it could be 0.1, somewhere it could be 0.05, somewhere it could be 0.2. But the probability, the sum of all the probability has to be 1. So the second condition we put is that the probability of finding the particle in the entire space should be 1. And that is what is normalization all about. So let's put that and get the value of a. Now, so psi into psi, it's not psi divided by psi, by the way, it's psi into psi, which is psi star dx. Going from 0 to a has to be 1. So we know this to be true, and we are going to use this now. So I can write psi square dx, because psi star is virtually psi square, but we know the interpretation of psi square. Since psi of x is a sin x, remember, a sin kx, this was what we got by putting those boundary conditions. So we will substitute the value of psi here. Psi square becomes a square sin square kx. I take the a square outside. And what is sin square theta? Sin square theta is 1 minus cos 2 theta by 2. So I integrate that within this space. So I can take the 1 by 2 separately and cos 2 kx by 2 separately. So a square is integral of half dx from 0 to a, and integral of cos 2 kx by 2 from 0 to a, and the sum of this has to be 1. Now when you integrate half dx, you get x by 2, and cos 2 kx is going to be negative. The integral of cos is sine, because the differential of sine is cos, remember. So cos 2 kx will become sine 2 kx by 4, because you have to divide by the derivative of this. So that would be 4. That will again come out to be 2, and 2 and 2 will become 4. Now let's put the limits. When you put the limits, this becomes 0 is gone anyway, and here also 0 is gone. So we only need to put a everywhere. So can you see I get this? And we know that Ka is n pi. Remember? So put this n pi here. Since n pi is 0, sine 2 n pi will also be 0. So see, any value of n pi is 0. Sine of n pi is 0. N you put as 1, 2, 3, 4, 5, 6, anything. So if n pi is 0, sine 2 n pi will also be 0. So it will be a square a by 2 equal to 1. Meaning this term will always be 0 for any value of n. So only a by 2 will remain. So a square a by 2 equal to 1. And what does that give you? A as root of 2 by a. So what is my wave function now? It is a sine kx. A is root of 2 by a sine kx. And if I substitute the value of k, n pi by ax. Now, when n equal to 1, we get psi 1. Each of these wave functions has an associated energy called eigenenergies. And now, what we need to understand here is that you will say, okay, still we are getting multiple wave functions. Of course, you will get multiple wave functions, because the energy of the electron is not one fixed energy. At one position, it will be one. At another position, it could be something else. But there are discrete values of energies, which is what Niels Bohr said in an atom. There are discrete energies. When n is equal to 1, there is a particular energy. N is equal to 2, there is a certain particular energy. But in between these two, there is no energy. In between these two energies, there is no energy. So now let's remember, k square is 2me upon h bar square. So what does E come out to be? H bar square k square by 2m. And if I were to substitute the h bar square and k as n pi by a, okay, I can keep h bar square as it is, I guess. And k is n square pi square by a square. So for each value of n, we will get a unique or eigenvalue of energy for a particle in a box. So this is the solution of the Schrodinger equation of the simplest system of a particle in a box in one dimension, and where we are looking at the time independent version. So I hope you're able to get the basic hang of it. You can watch this video as much as you want. And as you have noticed that I've tried to change the video a little bit. I've tried to put less text on my slides and more of mathematical information, and whatever text that I wanted to convey using the slides, I would probably talk to you, look into your eye and talk to you, and that would probably be a better way of dealing with the theoretical part of this. And as I said, when I'm going to make my design my website, I'll put all the particular notes with the theoretical part of whatever I have said. So having said that, there's a couple of more things that we need to get right. If we want to calculate the probability of finding the electron at a point in space, then we calculate psi star. Okay. If we want to calculate the probability of finding the electron at a distance dr from the nucleus, then we calculate psi star dr. So what is the meaning is at a point it is psi star. But if you say, okay, I want it at a point dr from the nucleus with reference to the nucleus. At any point it is psi star. The psi at that point into psi star at that point. But if you say, okay, at this particular distance, how much is it? So psi star dr. And similarly, if it is at a certain volume dV from the nucleus, well, psi star dV. So if you want to calculate the probability of finding the electron in a volume dV around the nucleus, then it is psi star dV. This is applicable only in a three-dimensional system. And that is the end of 12C. So I hope you were able to understand whatever I was trying to convey in this video. If there are any questions, anything that is not clear, please put them in the comment section below. I hope you enjoy videos like this. Try and share these videos with your friends, your colleagues. This can help all of these people and help us grow this particular channel. And make sure that all of them subscribe, because I've noticed 80% of the traffic in this channel is of people who visit the channel, see the video, sometimes even appreciate it, but do not subscribe to it. So make sure they subscribe, because the more you subscribe, the more motivation we feel and the more easily and frequently we're able to make videos. With that, this is Kalyan Kumar signing off. Have a wonderful and a great day, and thank you for watching this.